we're going to define a special matrix operation called matrix transpose. Definition, well, if I give you an m by n matrix, the transpose of that basically has the rows and the columns flip-flopped. So the rows of A become the columns of A transpose. Now, as an example here, I've color-coded a 3x2 matrix A, and we take the first column of A and it becomes the first row of A transpose. Second column of A becomes the second row of A transpose. Now you can see that necessarily the dimensions of A and A transpose can't be the same. In general, the only time they'll ever be the same is when you've got a square matrix. Now, once you've got transpose defined, it's pretty easy to do the usual rules of matrix algebra, adding, subtracting, etc. However, there are some properties that we should mention just for thoroughness sake. Some we'll prove, some we won't. Some things like the transpose of a sum ends up being the sum of transposes. That's not very interesting, but it's useful. If we ever have a scalar multiple of a matrix and we want its transpose, you could think of it sort of on an entry by entry basis, right? If I give you a scalar multiple of a matrix, that means every single entry in that matrix is being scaled by this factor. And if I were to transpose this, you could see that I'm basically just taking that top row SA11 and then making it the first column. Now, the point here is that every single entry still has this factor of S. And you could take it out, and what you'd be left with is basically A transpose there. So you can pull a scalar multiple out of a transpose. So if I were to take AB, we've discussed the idea that we could write a matrix in terms of rows. So perhaps this matrix can be written like this in terms of its rows. And then sometimes this matrix here can be written in terms of its columns. And so when we do a matrix multiplication, what we're doing is essentially taking the first row, multiplying by the first column, and then that becomes our entry here, A1 dotted with B1. And this pattern continues all the way down the line, A1 dotted with Bn. And you could continue this for every single entry that you're doing. So now, because we've got a dot product, it doesn't matter which way we write the order of these things. So if I wanted to, I could put the B in the front. Now, why do you care? What difference does it make? It's going to make a difference when we get to this transposition idea. So if I now want to take the transpose of this, I am going to flip the first row, make it into the first column. So I'll have a B1 dotted with A1, and then that'll go down Bn A1, and then this will go across B1 dotted with AM, Bn dotted with AM. Thinking of it this way, we can see that we've got essentially the same result we had, but just with different entries. So we'll have B1 all the way down to Bn over here, multiplying this matrix with column A1 all the way down to column AM. And again, you can see that if we do this whole idea, top row, first column, that'll get us to this entry. Top row all the way down to the last column, that'll get us to there. And the point of the story here is that this is B transpose times A transpose. So that's an interesting result. Not obvious, but needs a little bit of care. B transpose A transpose.